Imagine a world without sound. The world would be so different. No music, no alarm clocks, no conversations. Now let's turn up the volume. What do you hear now? So what is sound? The concept of sound was first mentioned by Pythagoras, a Greek mathematician who noticed the correlation between the length of a string and the tone it produced. Jean-Baptiste Fourier, a French scientist, later discovered that complex waves, several sounds put together, were just simple periodical waves. Much work was later done in the 19th century concerning acoustics and actual and perceived waves. So sound is a vibration. In other words, it is a wave that travels through mediums such as a solid, liquid, or gas, thus making it perhaps audible to the recipients of these waves. One way of perceiving how sound waves pass through a medium can be by observing how the slinky vibrates and moves in a certain direction when I push it down the stairs. Notice the sound that is emitted from the slinky as it falls like a wave down the stairs. Since sound waves depend on its interaction with a certain medium, there cannot be sound in space, as space is a vacuum. This is how a battle would really look like in space. But this would make for a pretty boring movie, so movie makers of classic space movies have you hear sound. Of course, this is not realistically what happens in space. Again, why don't we hear sound in space? Because there is no matter in space to transmit the sound waves created by the objects in space. So, how does sound travel in different mediums on our planet Earth? In 1640, another French mathematician, Marin Mersenne, did experiments to try to define the speed of sound in air. He discovered that a sound was a wave transmitted through a medium. Through further experiments, scientists have confirmed that the speed of sound is not constant for different mediums, thus accounting for different sounds. The speed of sound depends primarily on the rigidity and density of the medium. Scientists have thus determined this formula for calculating the speed of sound, where v, the speed of sound, is equal to the square root of a concept called the bulk modulus, or how hard it is to compress the object, divided by rho, or the density of the object. In other words, how much mass per volume is in the object. The more rigid a material is in relation to its density, the faster a sound will travel. This is due to the strong intermolecular connections within the medium, so that any vibration through that medium is transmitted faster. So, the speed of sound in a solid is generally faster than for a liquid, and the speed of sound in a liquid is generally faster than in a gas. I'll just quickly mention too that temperature can also play a factor, particularly for gases, as the hotter material is, faster sound will travel through it as the material becomes less dense. The same would go for the effect of pressure on gas. Check out my last video on this science video channel to learn more about air pressure. So, how fast can sound be? Well, first, we all know it is nowhere near the speed of light, which is 299,792,458 meters per second. How can you tell? You always see lightning before you hear the thunder. Let's take a look now at how sound travels through different media. Again, the speed of sound varies depending on which medium it is transferred through. Scientists have measured that in the air at sea level at 15 degrees Celsius, sound travels at 340.29 meters per second. In water at 20 degrees Celsius, sound travels at 1,481 meters per second. In titanium at room temperature, sound travels at 6,010 meters per second, and at 12,860 meters per second in beryllium. Still, it is nowhere near the speed of light. Let's now compare four cells the speed of sound for a solid, a liquid, and then the air. Have you ever played telephone when you were little? Let's take two plastic cups, a needle, and Fred, and 2 small wooden sticks. Pierce the bottom of the cups with a needle and thread, and tie the end of the thread at the bottom of each of the cups to each of the wooden sticks. The longer the thread, the more fun this can be, but make sure that you keep the thread taut, so that the sound wave can travel in a straight path from one end of the thread to the other. When you're done tying the thread to each of the wooden sticks inside each of the plastic cups, one person can talk into the cup and the other person can press his or her ear against the cup to listen to the person on the other end, blocking his other ear with his hand. You can hear that person even though that person is not even in the room with you. If that person talks at the same modulation without this type of telephone, you should notice that you can't hear that person as well. Through the cotton thread of our homemade telephone, sound is traveled faster than through the air alone, which is why you should be able to hear through your homemade telephone better than without it. Try experimenting with a metallic thread, or even paper cupped, and see whether you hear a difference. Now let's look at sound traveling through water. Can you hear something? At about 100 meters away, we finally see what was making this sound. Outside the water, we couldn't hear a sound as well, even though we could see the whale at about the same distance. Let's recap now how sound travels. Sound is a wave traveling through a particular medium: a solid, liquid, or gas. The speed of sound depends on the rigidity and density of the medium. This means that sound will generally travel faster through a solid than through a liquid, and it generally travels faster through a liquid than through a gas. But again, it depends on how rigid and dense those different mediums are. As you travel yourself, enjoy the sounds of the world around you.